Hi, this is Mr. Colati, and today we're going to be going through section 3.3, which is Newton's first law. You can go through the lecture slides yourself, but basically Newton's law states that an object at rest tends to stay at rest, and an object moving at a constant velocity tends to stay at a constant velocity, unless acted on by an external net unbalanced force. You're going to go through that and write out that word for word. The words are very important. And you're going to go through some of the implications and special cases of that, some of the more conceptual ideas. But I'm going to go through these two examples with you. Now, the first example is drawing free body diagrams. The first question, a hockey puck is sitting at a table. Well, okay, so I have a hockey puck. I'm going to represent it as a dot. It has a force of gravity acting down. And because it's sitting on a table, it's not falling down. The table is pushing back up at it. This is a normal force. Is this an example of Newton's first law? Yes. The object is at rest. Or another way of verifying it is the forces are balanced. You can see often we'll put these little lines here to show that they're the same length, just like we would do when we draw triangles that have the same side length. Because they're balanced, this is Newton's first law. Because the object's not moving, it's also Newton's first law. Second example, a person is pushing a hockey puck forward on a table at a constant speed. Okay, well, I have my hockey puck, so first of all I'm going to draw gravity again and draw that normal force again. This time somebody's pushing the hockey puck, so they're applying a force, Fa. Now we know the hockey puck is moving at a constant speed. If it's moving at a constant speed, it has to be Newton's first law. If it has to be Newton's first law, then all the forces need to be balanced. Well, these two are balanced, but what's balancing the applied force? Well, there has to be something here. What force would oppose me? Well, it would have to be a kinetic friction force. You can imagine this, right? If there was a hockey puck on the table, I can push it at a constant speed. I can push it at a speed that will ensure that the friction and my applied force balance perfectly. So yes, the object moves at a constant speed. In terms of free body diagrams, if an object is at rest or moving at a constant speed, these are both examples of the first law. And in terms of free body diagrams, the forces are balanced in both cases. What happens when the forces are unbalanced? That's tomorrow's lesson, which is on Newton's second law. Part C. A hockey puck is sliding forward at a constant speed on a friction-free ice surface. So here I have the force of gravity again for the same puck. There's a surface, so it's a normal force. It's sliding forward at a constant speed. Okay, is anyone pushing it? No. Is there any friction? No. So we're done. This is also an object moving at a constant speed. The forces are balanced. So this is another example of Newton's first law. Newton's first law says an object will stay at rest. This hockey puck sitting here will stay at rest. This hockey puck, it also says an object moving at constant velocity will stay at a constant velocity. So this hockey puck sliding on a friction-free surface, if there is truly no friction, then this hockey puck will continue to move forever. Now the reality is we don't have an absolutely friction-free surface. Even an ice rink has a little bit of friction. That little bit of friction will slow down the hockey puck eventually. But theoretically, if I had a friction-free ice surface, a balanced forces means that this is Newton's first law. Newton's first law says that an object in motion will stay in motion unless acted on by an outside force. So that's kind of three interesting examples of how free body diagrams apply to Newton's first law. Let's move on to this example. Mark and his friend Al are trying to move a cart with mass 25. Mark pulls the cart with a force of 28 newtons. The kinetic friction is this. If the cart is moving west at a constant velocity, determine Al's normal applied force and the normal force. Okay, well, let's start with the free body diagram. That's my most important thing. The first thing I know is that there's a force of gravity here. That's on my cart. I also know that this cart, the force of gravity is balanced by a normal force because it's on a surface. Now, Mark is pulling, he's pulling the cart west, so he's pulling it this way. We're going to call that applied force. We'll call it applied force 1 because we know that Mark has a friend helping out. The friend is also pulling in the same direction or pushing in the same direction. That's going to be FA2, but we don't know what that is. And we know that there's friction, kinetic friction, at 41 newtons, and that's going to be going the opposite direction. Now here's the real important thing. If the cart is moving west at a constant velocity, this tells me that it's the Newton's first law. That means the forces must be balanced. Therefore, these two forces have to be balanced by one long force this way, which we know to be kinetic friction 28. 41 newtons east. Let's do some declarations here. This is going to be positive up, and we'll call this positive west. So therefore, this is positive 28, and this is negative 41. Now we have a formula for calculating force of gravity. If you'll remember from the first day we did forces, this is m times g. This is a way of calculating the force of gravity for any object. You take the mass of the object, and you multiply it by 9.8, the acceleration due to gravity. We haven't really dealt with this formula a lot. We're going to do a whole lesson on it in chapter 4. So don't worry about it too much for now. Just know that it's always possible to calculate the force of gravity if you know the mass. If I type this into my calculator, I've already done it, I get 245 newtons down. Because I declared up as positive, I'm going to write this as negative 245. Okay, now, what is Al's applied force? Well, there's Mark's force, so I want to find out what Al's applied force is. Well, I know these are balanced. Because the forces in the x direction are balanced, well then therefore my F net in the x direction is equal to 0. In other words, FA1 plus FA2 plus FK is equal to 0. Now when I add these three vectors, I have to consider direction. FA1 is positive 28. FA2 is, well, I don't know what it is. That's what I'm trying to find out. And FK is minus 41. Is equal to 0. Now when I solve this, I end up with FA2 is equal to 41 minus 28. So I get 13 newtons. And it's a positive number, which makes sense because we know he's moving this way. Therefore, his force is 13 newtons to the west. For part B, similarly, to find the normal force, I know that these two forces are balanced. So I know that my net force in the y direction is equal to 0. In other words, Fg plus Fn is equal to 0. In other words, Fn is equal to 245 newtons up, because it has to balance this 245 newtons down. I hope that helps you understand Newton's first law. It is a little confusing, this idea that something moving at a constant speed has to be have balanced forces. Good luck doing the problems, and we'll see you next time.